This is a calorimetry problem with a phase change, and the phase change is uncertain. We don't know if all of the steam condenses. So what we need to find out is, is if the final temperature is greater than 100, then we don't have to worry about phase changes at all. Well, I guess we do. We have to worry about the water heating up. If the final temperature is 100, then not all the steam condenses. And if the final temperature is less than 100, then all the steam condenses, and we have to find the final temperature. So before we really start this problem, we have to figure out which of these three domains we're in. So first of all, I'm going to find out how much heat it takes to condense the steam, to condense all of the steam. So first we have to cool the steam down to 100 degrees. The specific heat of steam is 2010, and it's going from final temperature is 100, the initial temperature is 160, so delta T is minus 60. And then we have to condense the steam. Now that's MLV, and it's minus because we're losing heat. So that's 2.26 million. Okay, so that's minus 7839 minus 146,900, which equals minus 154,739. So that's how much energy it takes to condense all the steam. Now let's see how much energy it takes to heat the aluminum and the water up to 100. Okay, so that's for the aluminum, it's 1.2 times 900, and now we're at TF minus 22. TF is 100 in this case, plus for the water times the same delta T. So that's 84,240 plus 81,627, which works out to 165,867. So it looks like there's plenty of energy available in the water to condense all the steam, right? Since 165,867 is greater than the 154,739, that means all steam condenses, and our final temperature is going to be below 100 degrees. Okay, and we don't know what the final temperature is. We have to find TF. Okay, so now this is a calorimetry problem, right? It's just delta Q for the steam plus delta Q for the aluminum plus delta Q for the water is equal to 0. I know it looks like we're starting over, but we're not, because we've already calculated a lot of stuff we need, as you will see. So delta Q for the steam, we have to condense the steam, and then we have to cool the steam to some final temperature. Okay, and then we have to heat the water and the aluminum to that same final temperature. Okay, so to condense the steam, well, we already know how much energy that takes. That's minus 154,739, right? That cools the steam down to 100 and condenses it. To cool the steam to the final temperature, we're going to use this, 0.065. Now the steam is water, so it's 4186, and then we use TF minus 100. Okay, we start, our initial temperature for this step is 100. Right? We already went down to 100 up here. We went from 160 down to 100. You cannot use 160 here. You're only going the last little bit. And then to heat the water and the aluminum, that's going to be for the water, or for the aluminum, it's 1.2 times 900 times TF minus 22. And for the water, it's 0.250 times 4186 times TF minus 22. Okay, so that all sums to 0. Alright, so now I've got to expand all this stuff out. So bear with me. Okay, so this entire term right here is delta Q for the steam, right? So this part here condenses or cools the steam down to 100 and condenses it into water, and then this part right here cools the steam down to whatever its final temperature is going to be. And then for the aluminum, we have 1080 TF minus 23,760, and then for the water, it's 1046.5 TF minus 23,023. Alright, so combining, I'm going to combine all of my constant, or all of my just integers, my numbers. So there's that, there's that, there's that, and there's that. Those all add up to minus 228,731. Now I'm going to combine all my terms that have TF in them, here, here, and here. That's plus 2398.59 TF. And if I solve for TF, that's positive 228,731 over 2398.59. That's 95 degrees Celsius. That's less than 100. It's greater than the initial temperature of the water and the aluminum. So it's a reasonable, and it's only a little bit less than 100. That makes sense because we were only a little bit different here in our heats. So it's a sensible answer.